All right, so this is going to be section P3 of the book. We're only going to do part of it today, so we'll be doing this section over the course of a few weeks. So this section is where we start working with functions and visualizing them. All right, so by that, we mean the graph. Okay, so the graph of a function, we're going to use it to kind of have a visual picture of how the function behaves. So how does a graph work? Well, if you have a function, a graph would look something like this. So let's say this is the graph of f of x. So the way you read this is the x-axis represents the inputs to your function. The y-axis represents the outputs. And so let me mark a few numbers here, 2, 3, 4, let's say 1, 2, 3. So for example, if you, for this particular function here, whose graph is given right there, if you plug in 2 into your function, right, what you do is you go up vertically from the input 2, you hit the graph, and then you go horizontally until you hit the y-axis. All right, where you hit the y-axis, that's the output. So this is the input, that's the output. All right, so for this particular graph that I've drawn, f of 2 is equal to 1. All right. Okay, another example. If I look at the input of 1, then again, I go vertically up until I hit the graph, and then I go horizontally until I hit the y-axis. And the position on the y-axis right there is going to be the output. All right. So perhaps this one looks like f of 1 is just under 3, between 3 and 2, right? So maybe we write it like this, between 3 and 2. All right. Graphs of functions are great because you can kind of encode all the information about the function just in kind of, a curvy line here, right? If you ask me what f of any number is, I can, kind of figure it out just by doing this procedure that we did right here, right? F of 2.5 is going to be some number less than 1, all right? Okay, so ideally, we would always want to have the graphs of our function, or we would always want a picture of the graph of our function. But in reality, most of the time, the graphs are too difficult to reproduce from the formula. So most of the time in real life, what you'll have is a formula, f of x equals something. We'll talk about this one in the near future, sine x, right? And from this formula, you would like to draw the graph. So the graph is going to look something like this. But it's actually very, very hard. This is something that if you go on to take calculus, it's a major section in calculus, how to go from a formula to a graph. And again, once you have a graph, you have an enormous amount of information about the function. All right, so let's talk about the graphs of a few kind of core foundational functions. We're not going to explain where those graphs come from. Again, you will, if you take calculus, you will be learning exactly that. But let's give a few kind of core examples. So f of x equals x squared. So the graph of this guy looks like that. So this is a parabola. That's terrible here. Let me write it here. And these two arrows here represent that it continues, but it continues on and on. But obviously, we can't draw an infinite amount of the curve. So here, just from looking at this graph, we can recognize a few important features of this particular function. So, for example, it's never negative, right? Because anytime you have an input, you always go up to hit the graph. And so the y-coordinate corresponding to that is always a positive number, right? Whether you're on the right side or on the left side, you're always going up, and then that's your output. So your output is always going to be a positive number. So again, this is something that you typically want to notice when you see the graph of a function, if it's something that is a feature of that function. So let me just write this as note. F of x is always bigger than or equal to 0. And again, of course this is true because your function is f of x equals x squared, and x squared can never be negative. But again, we're trying to kind of recognize this information just from looking at the graph. All right, another kind of interesting feature is that the minimum, the smallest value, the smallest output possible is 0, right? And in fact, f of 0 is equal to 0, right? So if I input 0, I actually don't even have to move. The output is right there, okay? So that's, again, a good feature to notice. The maximums and minimum values that a function can achieve is super, super important. And that's another thing that if you are going to take calculus, you spend a lot of time on, where you have a function given as a formula and you want to figure out where its maximum and minimum is. So in those situations, you'll only have a formula and you won't have a graph. And so it's actually very difficult. But you can see here, if you do have a graph, right, you can literally just instantly see where the function is a minimum. Okay, so again, that's the power of having the picture, having the graph of a function. This particular function, there is no maximum value because whatever x I put in, right, I'm going to get an output y. But if I go further to the right, I'm going to get a bigger output y. All right, I'm going to pause here for the garbage. All right, no biggest output, right? Because whatever you claim is the biggest output, I can always find an output that's even bigger. That's the kind of official reasoning. All right, another feature of this function is that it's symmetric about the y-axis, right? In that this right-hand side is actually a mirror of the left-hand side. All right, it looks exactly the same. Okay, and again, in terms of the formula, it makes perfect sense because, for example, if I plug in 2, my output is, well, x squared, so my output is 4. But if I plug in minus 2 right on the opposite side of the y-axis, if I plug in minus 2, I'm going to get the same number, output 4. All right, so the left and right sides are symmetric. That's actually a very, very important feature of any function if it does have that feature. So you always want to try to notice this kind of symmetry. All right, sorry. All right, so our class is Trig, but so we're not really going to be working with parabola very much in our class. But these examples here kind of demonstrate general features of functions, and you will certainly be using them in the future in future math classes. And also, when we do talk about the graphs of the trig functions, which we will very soon, they're going to have a lot of this, the same features. For example, cosine is going to have this symmetry feature. So it's good to kind of see them perhaps in kind of a more simple form, right? A function f of x equals x squared is a fairly simple function. All right, let's look at another one. F of x equals square root of x. So this guy looks like that, and it keeps going on and on forever. So this one is kind of interesting in that there's nothing on the left-hand side here. There's no portion of the graph. I didn't draw any of the graph to the left of the y-axis, and that's because, well, if you try to plug in any number here, right, that would be a negative number, and so you would be taking square root of a negative number, and so that's definitely not allowed. And so, well, at least for our class at this moment, in the future, we will be, in a way, allowed to, but not right now. And so there is no output. So this input here corresponds to nothing. There is no output. And so there's no portion of the graph above or below this point right there. All right, so the only legal inputs for this function are everything from 0 and to the right, right? So the input of 4 is perfectly legal, the input of 5 is perfectly legal, but nothing to the left of the y-axis. Okay, the shape of f of x equals square root x contrasts with the shape of the parabola. One thing you'll notice is that the parabola grows very fast, right? So let me actually draw the parabola down here again. So the parabola looks like this. So it grows very fast, right? When you plug in a number here, when you put in an input here, you get a number there. When you go to the right, you get a much bigger number. When you go farther to the right, you get a much bigger number, and so on. Whereas the square root, you do get bigger numbers as you go to the right, but the numbers aren't as big. Okay, so the square root function is a function that grows very slowly compared to, for example, the parabola. In fact, let me actually draw them both on the same picture. So here's the square root function, and here's the parabola function, right? So what happens is for inputs less than that number right there, which is actually 1, right? Because for the parabola, right, if you plug in 1, you get the output 1 squared, which is 1, right? And for the square root function, if you plug in 1, the output is square root of 1, which is also 1. So the two graphs actually intersect right there. Okay. For numbers, for inputs less than 1, the parabola actually gives, or the f of x equals x squared gives smaller outputs than the square root function, right? So for example, if this is 1/2, then 1/2 squared is only a quarter, whereas square root of 1/2 is bigger than a quarter. Okay, so that's how you can read information if you draw two graphs in the same, two functions, the graphs of two functions in the same picture. In contrast, if I put in any number to the right of 1, the square root will be here, whereas the parabola will output a number up there. Let me extend this a little bit. The output will be a number up here. So what that indicates is that to the right of 1, whatever you plug in, the square root is going to be smaller than x squared, right? Which makes sense again, because for example, if I plug in x equals 4, square root of that is 2, but 4 squared is 16, so much, much bigger. Okay. All right. I know a lot of people in this class are eventually going to be taking calculus. There's another really, really interesting feature of the square root function, and that's that at 0, it kind of goes upwards vertically in a way like that. Okay, but you'll deal with that in calculus. All right, another function, f of x equals x cubed. So this one looks like that, and then like that. All right. So this one, you can, in contrast to the square root function, you can plug in any number, right? Any number, any input is legal. I can plug in 2, right? If I plug in 2, my output is going to be that number right there, which is, of course, if I calculate it, it's going to be 8. Or I can plug in -2. My output is going to be, well, -2 cubed is -2 times -2 times -2. You've got 3 minus signs, so that's going to be -8. All right, so let me label these 2, 2, -8, 8. And you can see that this actual pattern holds for any input, right? If I put a number in here, I'm going to get some output there. But if I put the same number here on the opposite side, sorry, that's -2, on the opposite side of the y-axis, so the negative version of this number, I'm going to get the same number but negative. All right, so this function is what we're going to be calling an odd function. So it has a symmetry, but not kind of a direct mirror symmetry like f of x equals x squared. All right, this function also has an interesting feature at 0. When you plug in 0, you get the output 0. And actually, it looks kind of flat right there. And that's super interesting in terms of calculus. All right, let me just write down here. This is what we call an odd function. We'll go into this a lot more carefully in the near future because The cosine function, which we'll talk about again in the near future, is also an example. Sorry, the sine function is also an example of an odd function. Okay, and this function here grows really, really fast because, well, you're cubing your input, except for when you're less than 1, in which case it gets smaller. All right, a couple more. So f of x equals 1 over x. That looks like this, and like that. So what happens is, for example, when you plug in a negative number, right, you're going to get the negative version of the output compared to if you plug it in a positive number. Because of course, for example, if you plug in 3, you're going to get 1 over 3. If you plug in minus 3, you're going to get minus 1 over 3. So this guy is also an odd function. Again, we'll be comparing that to sine, the sine function in the future. All right, this guy also has some other interesting features. As you plug in bigger and bigger inputs, the output gets smaller and smaller and smaller, right? And that makes sense, right? For example, if I plug in 10, I get the output 1 over 10, which is 0.1. If I plug in 100, right, which is much bigger than 10, I get the output 1 over 100, which is 0.01, which is much smaller than 0.1. So as I plug in numbers to the right of the x-axis, my outputs get smaller and smaller and smaller. Okay, so this graph here approaches the height of 0, but it never touches the height of 0 because there's no input you could plug in that gives you the output 0, right? 1 over anything is not 0. It could be really, really small, but it's never 0. All right, so these are called horizontal asymptotes. And we'll be looking at arctangent in the future, and that will have horizontal asymptotes. Okay, another feature when you let me write over here horizontal. Okay, so another way to say this is that there's a horizontal line that the graph approaches as you input bigger and bigger numbers, or more and more negative numbers to the left here. Okay, but it also has a vertical asymptote. And what that means is that as there's a vertical line right there, that if you plug in inputs closer and closer and closer to that x value right there, which is x equals 0 in this case, your outputs get taller and taller and taller, bigger and bigger and bigger, right? And that makes sense because when I plug in smaller and smaller numbers into 1 over x, the 1 over makes it bigger and bigger, right? 1 over a half is 2. 1 over 1/3, right, which is smaller than a half, is 3, right? So as I plug in numbers that get closer and closer and closer to 0, my outputs get bigger and bigger and bigger. Okay, and I can never plug in 0 because 1 over 0 doesn't make sense. All right, so this is also interesting because for our class, because the tangent function will have vertical asymptotes, a lot of them. By the way, just as an interesting note, this function has no maximum or minimum output because whatever you claim is the maximum output, I can give you a number which is even bigger. That's also an output, right? And whatever number you claim is the smallest possible output, I can give you a number that if you input it, it gives you an even smaller number. Okay, finally, we have f of x equals mx plus b, and this is a line whose y-intercept is at height b, and whose slope is m. So let's draw a picture where the slope is positive. All right, so maybe perhaps this is f of x equals 3x plus 10, something like that. All right, so this one's interesting because it's just a straight line. All right, we'll be talking about lines a bit more in the future, so I'm not going to dwell on this one, but this is in a way one of the most simple functions that you can play with because it's just a straight line. And being just a straight line means it's really, really useful in calculus, for example, in approximating kind of more ugly functions. All right, so that's kind of an introduction to kind of graphs of a few functions. I guess I should mention one thing. We said that last time that a function is something is like a machine where you put in an input and you get one output. And we said that the only real kind of restriction here is that when you put one thing in, you get one thing out. There should be no ambiguity as to what the output should be. All right. So something like this cannot be a function, cannot be the graph of a function, because if you try to kind of interpret it that way, then this input there will result in what output? Well, if I think about it, it makes sense to say that this is my output right there, right? But it also makes sense to say that this is my output right there, right? Again, I'm going up until I hit the graph, and then I'm going horizontally until I hit the y-axis. So both the blue and the red make sense, right, in terms of what the output should be. And in fact, there's even one more at the same point, right? That I could also argue that that should be the output. Okay, so this is not legal. It's the only thing that's not legal. When you have one input, you should only have one output. All right, there should be no question as to what that output is, right? And what we've seen in all our examples up here is that's exactly the case, right? If I put in an input here, there's no question what the output is. The output is that number right there. If I put in this guy right there, there's no question as to what the output is. The output is that guy, that number right there. Okay, so this guy here is not a function, not the graph of a function. And these guys are very terrible to work with because, especially in calculus, because calculus is all about understanding functions in a way, and how functions change. So if you have something which is not a function, in a way, it's very difficult for you to do calculus. And calculus is essentially the thing that solves all problems in the world. Physics, biology, economics, almost literally everything. Okay, so let's talk about kind of the interesting, more difficult material in this section, and that's modifications of functions. So, for example, let's say I have a function f of x, all right, and I want to modify this function. So I'm going to create a new function. So let's create a new function g of x, and the kind of output of g of x is going to be, it's going to depend on the output of f of x. So g of x is equal to, f of x plus 3. All right, so this is the definition of g of x. All right. So in other words, for example, what is g of 10? Right, g of 10 is equal to f of 10 plus 3. So it's f of 13. Okay, so if I had a formula for f, whatever this formula would be here, I could calculate g, right? Because whatever I plug in for g, I just add 3 to whatever I'm putting in, and then I plug that result into f. All right. Okay, this is a very, very common type of modification of a function. Like, again, where you're given a function, f of x, right? And you want to kind of change it in some way by creating a new function g of x, where the new function has kind of a slightly different input, right? The input is always x plus 3, right, in this case, into f when you input x into g. All right. Okay, I guess maybe I should give a concrete example, right? So if, for example, f of x is equal to x squared, g of x would be f of x plus 3. And in this particular example, what is f of x plus 3? Well, f is the function that whatever you put in, you should square it, right? So I'm putting in x plus 3, so I need to square it, x plus 3 squared. Okay, so this would actually be the formula for g of x in this example, okay? All right, we're going to be very, very interested in this kind of modification, this type of modification of a function, because, well, very soon we're going to be working with sines and cosines, and we really, in real life, it's very common to consider this kind of modification of sines and cosines. especially in terms of motion or circular motion, and those kinds of physical applications. All right, so the real question that we want to ask in this section today is if I did have if I did start out with a function f of x, and I kind of knew what its graph looked like, then the question is, what is the graph of g of x equals? Again, let me do f of x plus 3. What would the graph of this guy look like, right? So if I know this graph, oops, right? Then do I know this graph? Right, and it kind of makes sense as a question because if you know f of x, right, you have a lot of information about f of x, and g of x is only kind of a small deviation from f, and so it kind of makes sense that perhaps, you know, the graph of f can tell us what the graph of g looks like. All right, so let's kind of explore this. Let's say I know that, so I'm going to do this through example. Let's say I know that f of 5 is equal to 9. All right, whatever f's formula is, let's say I plugged it in. I plugged 5 into that formula, and I got the output 9. All right. Okay, so the question is, what do I know? What do I know about g? All right, and once we answer this question, we'll be able to answer the question as to what the graph of g looks like. And again, I'm using g of x equals f of x plus 3. All right. Okay, so let's explore. The only thing I know, right, right now is f of 5 equals 9. So what can I say about g? Is there anything I can say about g? Well, we can just kind of guess a couple things. Do I know g of 5? Let's see. What's g of 5? G of 5 would be equal to f of 5 plus 3, right? Just by definition of this g right there. And that's equal to f of 8, right? But I don't know f of 8. The only thing I know is f of 5, right? So this is equal to question mark. I have no idea. Okay, so this guy is not going to be very helpful. However, if I think about this, what happens if this thing in here, right, turned out to be 5, right? So if this thing in here turned out to be 5, then I would be looking at f of 5, and I know f of 5 is 9, right? So is there a number I can plug into g so that I get f of 5 in here, right? Well, I know that g of x is f of x plus 3. I want this thing in here to be 5, want this to be 5, right? So in essence, what I want is x plus 3 to be 5. So I want x plus 3 equals 5. And so now I just solved the algebra. So x is equal to 5 minus 3, which is 2. All right. So what this little bit of algebra told me was that if I look at g of 2, that's going to be f of x plus 3, f of x plus, x plus 3, right? So 2 plus 3. That's f of 5. And that happens to be exactly the one that I know. That's 9. All right. Okay, so let's think about, so this is the, let me say it like this. This is the only bit of information that we know about g, given that g has this formula here, and given that we know f of 5 is equal to 9. All right, now let me look at the kind of visual version of this. F of 5, let me use red for f. So f of 5, so here's 0. Let's say here's 5. I'm going to be interested in 2 as well. So f of 5 is equal to 9, right? So that guy right there is 9. Okay, so what that means is whatever the graph of f happens to be, it's going to have to pass through that point right there, right? So for example, maybe the graph of f looks like that, right? That makes sense because again, the input, you go up here, hit the graph, you go there, you get 9. And we know that, right? F of 5 is equal to 9. However, the graph of f cannot look like that because that would mean f of 5 is something bigger than 9. Okay? So the graph of f has to pass through that point right there. Okay, what do we know about g? G of 2 is 9, right? We just discovered this up here. So if I plug in 2 into g, I'm going to get the same output that I got for f. All right. So in essence, what happened was um, the graph of f, whatever it is, kind of got shifted over to the left to there in order to get the graph of g. All right. Again, this is the output for f. This here is the output for g. Right. So the output for g is shifted in a way to the left by 3 steps from the output of f. All right. So what this kind of indicates is that the graph of g of x equals f of x plus 3 is the same as the graph of f of x, except shifted over to the left by 3 steps. All right. So that's exactly what happened, in this picture here. Okay. So for example, let's say the graph of f looked like, here's 9, looked like that, right? Then that means the graph of g would have to look like exactly the same thing, except shifted to the left by 3 steps. All right. Okay, why 3 steps, or where did the 3 come from? This 3 is the same number as that 3 right there. All right, and the important thing to note is that it's shifted to the left. So if I do g of x is f of x plus 3, then I'm shifting to the left by 3 steps. All right. Okay, so for the functions that we know, for example, let's look at f of x equals x squared, right? Then if I have g of x is equal to, again, f of x plus 3, well, I know f of x is equal to a parabola, like that. So this is graph of f. Okay, then the graph of g is going to be shifted over 3 steps. Graph of g. Okay, and again, the difference is everything got moved over to the left by 3 steps. And so in particular, for example, before f of 0 was 0, and now g of minus 3 is equal to 0. All right. Okay, so the homework this week in terms of the online homework is going to be a lot of this. You'll be given a function, you'll be doing some modification for it, and they want you to graph the modification. So all my examples I've been doing g of x equals f of x plus 3, but the 3 isn't special. If I have f of x equals x cubed, and I say I want to look at g of x equals f of x plus 1, then f of x looks like that, right? Then g of x, the graph of g of x, would be shifted over 1 step to the left. So it would look like something like that. That's not very accurate. Something like that. All right, so everything is shifted to the left by 1 step. Okay, so in particular, f of 0 was 0, and now g of, if I shift it left 1 step, that means g of minus 1 is equal to 0. Okay, so you can ask what happens if we have, instead of a positive number here, we have a negative number. So if f of x is equal to square root of x, that looks like that. And g of x is equal to f of x minus 1. Well, the way to kind of remember this is that if it was plus 1, like in the example above, we're shifting to the left by 1 step. Now it's minus 1, so we're shifting to the left by minus 1 steps. But shifting to the left by minus 1 steps is the same as shifting to the right by plus 1 steps. Okay, so ultimately, this guy here is going to look like that. All right, and you can do the same kind of analysis in order to kind of really convince yourself of this by mimicking this analysis right here. All right, except with minus 1 right there, right? And what you'll notice is that to get the same output, the input would have to be shifted to the right. So here, our square root function, it's shifted to the right. Okay, so this is the only modification that we're going to be doing today. In this particular section, there's a few others, and we'll talk about those over the next few weeks. I want to do this one kind of slowly just because, number one, we have a little bit of time, and number two, this kind of graphing business, we're going to be doing it with the trig function, so it's really important to us, and so we want to make sure we get very comfortable with it. Let me mention what we're going to be doing in the future. So if I have f of x, in the future, we're going to be talking about other modifications. So if I have g of x is equal to f of x plus 3 outside, right? So this is outside the parentheses. Then it's going to be the graph is going to, of g is going to be related to the graph of f, but not by shifting left or right. Okay, so that's what we'll talk about in the future. I can also do another modification. Let me give it a different name. H of x is equal to, let's say, 3f of x, right? 3 times f of x like this. That's going to be yet another different modification. All right, and I can do p of x is equal to f of 3x. That's going to be yet a different modification. All right, so the one that we have today is kind of a very simple one. You just move to left or right. This one is going to involve moving up and down, and these guys are going to involve kind of scaling the function in some way. So we will be talking about how the graph behaves, right, as we change the function. In other words, how g of x behaves, how h of x behaves, how p of x behaves. All right, before we do that, let me kind of put this in words. So I have f of x, and I have g of x. Let's go back to our kind of core example, equals f of x plus 3. So what's the difference between f of x and g of x? So the difference is, to get from f of x to kind of g of x, let me put this in words. What we did was we replaced x by x plus 3. All right. So when you kind of find yourself using this word to describe a modification, then that means you have to shift to the left or the right. All right. So if I have a function f of x and I have another function h of x is equal to f of x minus 10, right? How do I get from this formula to that formula? What I did was I replaced x by x minus 10. Right? And let me give a kind of more concrete example. If f of x were x squared, right, and h of x were x minus 10 squared, right? What's the difference between these two formulas right there, right? The difference between x squared and x minus 10 squared. Well, the difference is every time I see a x in the original expression, I'm replacing it with x minus 10, right? So in the original expression, I have x squared. So now I have x minus 10 squared. Okay, so again, this is replace x by x minus 10. So I'm giving this kind of wordy description of our modification because what's going to happen in the near future is we'll have different word descriptions of this modification and this modification and this modification. And the words that you use is going to help you remember how the graph changes. All right. So for example, what we'll learn is that when you use the word replace in the modification, that means it's going to be the difference between the graph of f and the graph of g or h here is going to be something where you shift left or right or some sort of left and right change. Okay. We'll have different words to describe, for example, this one up here. And when you use those different words, it's going to mean that you want to change the graph of f up and down. All right. So what's going to ultimately happen is we're going to have complicated functions. So maybe we start out with sine of x. And ultimately, we want to know what the graph of 3 sine of x plus 10, right? Let me do this, 3x plus n, or let me, like that. And let me add something out here, plus 10. So what's going to happen is you're going to describe in words how to get from here to here. All right. Let me get rid of that 3 just to make it a little more simple. How to get from here to here. So for example, the way we're gonna do it is we're gonna say, well, to get from here to here, I first replace x with x plus 10. Okay. So if I started with sine x, now I have sine of x plus 10 because everywhere I see a x, I replace it with x plus 10. Okay. And then I'm going to say multiply 4 to the output. And we'll talk about this in the near future. Output. So what that means is I'm going to start with now my new function, this guy here. I'm going to multiply 4 to it. So what I had before was sine in the previous step, in step 1, x plus 10. Now we're looking at multiplying 4 to the output, right? So the output of this guy is sine of x plus 10. I'm going to multiply 4 to it. I'm going to get that, all right? And then step 3 is going to be add 10 to the output of the previous step, always referencing the previous step, all right? So my previous step, we ended up with 4 sine of x plus 10, and now we add 10 to the output. So this is going to be 4 sine x plus 10 plus 10, all right? And what's going to happen in terms of the graphing is when I see this word right there, replace, that means I'm going to take the graph of sine and I'm going to shift it over to the left by 10, all right? And that gives me the graph of this guy right there. And then when I see when I go to step 2, when I see this word, these words right here, that means I'm going to do something to the graph of x plus 10 to get the graph of 4 sine x plus 10. All right, I'm going to be stretching it vertically. We'll learn that soon. Okay, now I have the graph of this guy right there. All right, and so in step 3, I'm going to take the graph of the guy I just got. And then when I say add 10 to the output, that means that's going to mean I'm going to shift the graph that I just got, this guy right here, up to 10 spaces. All right, and so ultimately, after I've done these 3 steps, my final graph is going to be the graph of this guy up here, the one that we want. All right, so we're breaking down this kind of horrible looking function here into simpler 3-step pieces. And in each of the steps, we do a simple modification of our graph. And ultimately, after doing 3 modifications, we get the graph that we actually want. All right, so this is going to be an important part of working with trig functions, knowing exactly what they look like. And so we're going this a little slowly so that we can make sure that people are comfortable with it. All right, but again, at this moment, you can only do this step right there. And then these 2 steps we'll talk about again very, very soon. And of course, we'll be doing the same thing with sine of x, cosine of x, tangent of x. We can do it with any of the trig functions, as long as we know what the core trig function looks like, which again, we'll talk about very, very soon.